Welcome back, mathematicians. As you guys can see, these notes are already written today. Was that the plan? No. Did I record 2 hours and it just not show up? Yes. So the notes are written today. I have already gotten like one person's feedback that this is a little bit better. So here's a test too. So one-sided limits. We usually call it just the ordinary limit. That guy is just like a limit as x goes to some point c. We often call that limit the two-sided limit. Remember, it doesn't exist when there's a jump. So if we consider this function right here, f of x equal to x divided by the absolute value of x, we can look at its graph, and we know that the limit as x goes to 0 doesn't exist because there's this jump, right? If I approach 0 from the left, I am going towards -1. If I approach 0 from the right, the limit is 1. And I can write that down below here where I say the limit as x goes to zero with a negative in the superscript right here. I can then say that's equal to -1. And the limit as x goes to 0 with this plus superscript is going to 1. What that means is I can write down these definitions. So we say that the left-hand limit, I also call it LHL for shorthand, of f of x as x approaches c is LIM with x arrow c with a 0 in the superscript of f of x equal to L. We can also write that the right-hand limit, also abbreviated with RHL, of f of x as x approaches c is lim as x goes to c with a plus is a superscript of f of x equals m. So these are kind of a little tricky to focus on, and like maybe how do I remember if the negative's left, the positive's right? How I like to remember it, if I'm doing like the limit as x approaches c from the left, these points are all going to be less than c. So that's why there's a negative there. If I think those numbers are going to be smaller, I think minus is like a smaller kind of thing. And if I'm talking about the right-hand limit, those numbers that I can use to estimate the limit are all going to be numbers bigger than c. Bigger, like you can think of like the addition sign. So that's a fun way to think about it, okay? So now we can move on to an example. The function, the square root of 4 minus x squared, remember its domain is -2 to 2, and it looks like this. So its left-hand limit as I'm going down, oh no, I erased it. I don't think that was any better. As the limit as x is approaching -2 of f of x, I'm going down this function, I'm following it down. That point right here equals 0. Well, what if I'm going from the left-hand side, numbers that are smaller than -2? Can I do that? I actually can't. It does not exist. The reason why we can't use it is because there's no numbers less than -2. Those numbers don't exist. They're not in the domain of f of x. So that's why we can't use it. All right. So then we can't like plug in numbers to even test it. So it doesn't exist. So note that all limit laws that we just talked about in section 2.2, those all apply to left-hand and right-hand limits. So addition ones, multiplication ones, those are all the same. You can't mix and mingle left-hand limits and right-hand limits. So I can't if I have the left-hand limit of some function plus the right-hand limit of another function, those don't fly. It has to be the left-hand limit plus the same left-hand limit. Okay? So we have this theorem now that involves left-hand limits and right-hand limits. Remember how we said if there's no jump, the limit doesn't exist? This kind of is an explicit theorem for that. So we say that a function f has a limit as x approaches c if and only if, that's an important statement, the function has a left-hand limit and a right-hand limit there, and the one-sided limits are equal. So we say that the limit as x approaches c of f of x equals L, and this arrow means if and only if, the double way, the limit as x approaches c from the left of f of x equals L, and the limit from as x approaches c from the right of f of x also equals that same limit L. So I made a note about if and only if statements. They're very strong statements. That arrow going both ways means that if I have the limit as f of x equals x goes to c equals L, that means if I'm given that first statement, I can then say, oh, well, the left-hand limit and the right-hand limit both equal that same limit. Well, then if the other way the arrow points says that if I have that these two one-handed limits are equal to each other, then the two-sided limit also has to equal that same limit. So they basically imply each other and vice versa. So now I have a fun proof for you guys. Last lecture, I said that I couldn't really prove quite yet f of x equal to sine of theta over theta, that limit as theta goes to 0 equaling 1. So we can actually do it with one-sided limits. So I have already drawn this beautiful figure. Honestly, it's probably the best thing I've ever drawn. So we have this crazy picture. So what's going on is, let me change to something that makes me happier, pink. Okay, so I have the unit circle right here. This is the unit circle. That's not how you spell circle. Oh my God. Okay, circle. So that's what this black curve here is. Then I have this red line extending out to this point on my unit circle, P, and the purple line is the tangent line. You can see that it's tangent to the unit circle. And then, so that's why the purple is called tangent of theta. Let's see. Yellow is sine of theta. This black down the bottom is cosine of theta, and so on. So we have a point O at the origin, point P is on the unit circle, point S is on the tangent line, point R is where the unit circle and the tangent line intersect, and Q is where sine and cosine intersect. Okay, so this is the unit circle, so R is 1, R being the radius, not this point R. And we can kind of see by this beautiful picture, it really should be in the MoMA, the area of that triangle, O, R, and P, that triangle, so black, green, and red, the short red line, that area of that triangle is going to be smaller than the area of the sector that it's in. So that sector is kind of, if you think about the cheese part of the pizza, the sector is the cheese and the crust part of the pizza. It's the section of the unit circle. And then that sector and the triangle within it are all within the big red, purple, and black triangle. So I kind of drew them here at the bottom. So we have the small triangle that's in the middle of the sector, and then we have the big triangle, right? So, and those areas are all one less than each other. The area of the smaller triangle is less than the area of the sector, which is less than the area of the big triangle, because we can see graphically that they fit inside of each other. So I know that the area of a triangle is 1/2 base times height. So that's what I've written down here. And also the area of a sector, if you didn't know, it's 1/2 r squared times theta. So if I take, if I just focus on the triangle of O, P, and R, its height is sine theta. You can see that in yellow. The base of it is all the way over to R, which is the radius of the circle. And the sector's area is R squared and theta, which we don't know what theta is, and we know what R squared is. Oh, sorry, what R is. And for the bigger triangle, 1/2 base times height, our base here, again, is the radius, and the height is that purple line, which is tangent of theta. So we can plug in, since we know that we're dealing with the unit circle, that R is equal to 1. So I can then kind of plug and chug from there. So I now get that 1/2 sine theta is less than 1/2 theta, which is less than 1/2 tangent of theta. Alrighty? So then I can multiply each side by 2. So 2 times, 2 times, 2 times, right? What I do to one side, I have to do to all sides. And then I get sine of theta is less than theta, which is less than tangent of theta. And I'm going to divide by sine. This allows me to get, when I do that, sine divided by sine, that's just 1. And then I get theta divided by sine and tangent over sine. We know that tangent of theta equals sine theta divided by cosine of theta. And so that just means I have this whole thing divided by sine of theta. So the sines just will cancel out. And I'm left with 1 over cosine, because there's definitely like a 1 up there. Alrighty? Well, heck, I need sine of theta over theta, not theta over sine. So now I'm going to flip it. When I flip it, I also need to flip my inequalities. Right? If 2 is greater than 4, no, oh my god. 2 is less than 4, and I flip it, 1/2 is greater than 1/4. So when I flip my fractions upside down, I also need to flip my inequalities. So that's how we get that 1 is greater than sine of theta divided by theta, which is greater than cosine of theta. And then I rewrote it down here to show you how I can. Then I like to write it reading from smallest to greatest. So that's why I wrote cosine theta is less than sine theta divided by theta, which is less than 1. Well, I can then take the left-hand limit, right? 0, theta's, yeah, the limit as theta goes to 0, superscript negative. And I can apply that to each function. Because we were also given some limit laws back there that said, like, if a function f of x is always greater than or less or greater than or equal to g of x, the limit also has that property. So the limit of f of x is going to be greater than the limit of g of x. And that's kind of what we're doing here. Well, it is what we're doing here. So I know that the left-hand limit of cosine of theta, that's just 1, because theta, I can just plug in 0. Sine is like, the limit exists at theta goes to 0, so the left-hand limit is going to equal that, and that's how we get 1. We also know that a constant, its limit is just going to go to itself. So now I have that 1 is less than the limit as theta goes to 0 on the left-hand side of sine of theta divided by theta, which is less than 1. Well, sandwich theorem says that the limit as theta, the left-hand limit, as theta goes to 0 of sine of theta divided by theta, that has to equal 1, right? That's what the sandwich theorem says, like it like has to. So what about the right-hand limit, right? I did all that work for the left-hand limit. Am I going to have to like pull some other trig? There's so many trig identities, like what do? I actually don't have to do that. So that's like, bless up. So sine of theta is an odd function and theta is an odd function. Both of those are symmetric over the origin, right? This tells us that sine of theta over theta is actually even, right? An odd function divided by an odd function is even. Even functions are symmetric about the y-axis. About the y-axis. The y-axis is when x equals 0. Perfect. We're kind of looking at when our variable equals 0. So that means that theta, the left-hand limit of as theta goes to 0 of sine of theta over theta is going to equal the right-hand limit as theta goes to 0 of sine of theta over theta, which we know, we found the left-hand limit, r equals 1. Well, that's my definition up here, right? I have that these two equal. Well, that now tells me that this limit exists and it equals that same limit. So then we can conclude that sine of theta divided by theta as theta goes to 0 is equal to 1. Ta-da! So that's the whole proof. All right. So what's the point? Cool. Sine of theta over theta, it goes to 1. It's actually pretty useful in a lot of limits. So ones that you might not even think about. So our first example, we have the limit as h goes to 0 of cosine of h minus 1 divided by h. That doesn't have sine in it at all. Like, what am I supposed to do? So let's pop over to this red section right here where I've written the half angle formula. The half angle formula says that sine squared of h divided by 2 is equal to 1 minus cosine of h divided by 2. Well, I have cosine of h minus 1 in the numerator. This is 1 minus cosine of h over 2. So we have to do a little bit of rearranging. Don't freak out. It's totally fine. So actually, the first thing I do in blue is I'm gonna multiply each side by 2 because I want this 2 to go away. That gives me 2 sine squared of h divided by 2 equal to 1 minus cosine of h. Remember, I needed cosine of h minus 1. So I'm going to multiply each side by a negative 1, and that'll give me a cosine of h minus 1 is equal to negative 2 sine squared h divided by 2. This part is a little less intuitive than you might be comfortable with, so take a moment and read that over if you need to, or see if you can start at the half angle formula and get to cosine of h minus 1 by yourself. All right, so now I have cosine of h minus 1 from there, and I'm going to plug in, because they're equal to each other, to this limit. So now I have the limit as h goes to 0 of negative 2 sine squared h divided by 2 divided by h. So the limit, I can now take these pieces and multiply them in different parts, because when I'm multiplying fractions, I'm just going to multiply top times top and bottom times bottom. So when I separate these into 3 different fractions, I only can put an h in one of them, so I put it with 2, and you'll see for a second, and then sine of h over 2 times sine of h over 2, because it was squared. So then, I'm going to have, so now we have this negative 2 over h. If you see over here, I can show you that 2 divided by h is equal to 1 divided by h over 2, right? It's 1 over its reciprocal, right? So I can flip it and then write 1 over itself, and those two things are going to be equal. So that's how I got this 1 divided by h divided by 2 right there, right? And this negative is kind of annoying, so I actually move it to my second sine of h over 2, so that then on this line right here, I can write the limit as h goes to 0 of sine of h divided by 2 all over h divided by 2 times negative sine of h divided by 2. Okay? Well, I know that sine of theta over theta as theta goes to 0, that's 1, but now I have h divided by 2. So, well, let's just call theta h divided by 2, right? As h goes to 0, and theta is also going to go to 0, right? 0 over 2 is still 0. So then I can rewrite my limit as the limit of theta goes to 0, sine of theta divided by theta times a negative sine of theta. Cool. Product rule of limits says that I can multiply those limits together. So I know sine of theta over theta, that limit as theta goes to 0 is 1, and negative sine of theta will give me a negative 0. Multiply those together and we get 0 back out. All right? So what we kind of just saw up there was that the limit of something going to 0 of sine of something divided by that same something is going to equal 1. Right? It could be the limit as smiley face is going to 0 of sine of smiley face divided by smiley face. It's going to equal 1. Alrighty? So let's move on to example 2, and that'll be a kind of more linear example of it. So we have the limit as x goes to 0 of sine of 2x divided by 5 of x. 5x, not 5 of x, excuse me. So I know that sine of 2x over 2x as x goes to 0 is equal to 1. Notice that this is as x goes to 0, not 2x goes to 0. Those things are actually equivalent. Right, as x goes to 0, 2 of x goes to 0. So then this is what I want to get to. Something that looks like this. So I can pull out this 5 right here on the denominator, because right, fractions are numerator times numerator over denominator times denominator. That's how we can multiply fractions. So I just kind of pulled the 5 out of the denominator. Then I can multiply by what I call a fancy 1, right? Anything divided by itself is a fancy 1. In this case, I need a 2 right here. But I don't have a 2. I can't, 5 is not divisible by 2. I can't pull a 2 out of 5. So what I do is I multiply this whole fraction by 1. I can do that. Multiply anything by 1, it's just itself. So the 2 on the denominator down here is going to move to this x, and the 2 in the numerator is just going to join the 1/5 to the left. All right? It's multiplication, so I can do that, right? I can choose which order I multiply things. So now I have that the limit is x goes to 0 of 2 divided by 5 times sine of 2x divided by 2x. Well, that's what I wanted. I know limit law so that I can multiply the limit of this guy times the limit of this guy. So that's how I can get 2/5 times 1, right? Sine of 2x divided by 2x as x goes to 0 will give me 1. Multiply that again, and I can get 2/5. So you might be able to see a pattern with this. There's another pattern you'll see on your homework as well. So what if I just don't have, I've had it where I've had cosine, and now I have one with tangent. So I don't want to go there, yeah, right there. So this one's out of your textbook. Example 3 is, it's 2.4.25. And you're asked to find the limit as x goes to 0 of tangent of 2x divided by x. Right, so we've kind of mentioned this earlier in the lecture already. Tangent of 2x is equal to sine of 2x divided by cosine of 2x. Tangent is sine divided by cosine. So then I can plug that into my function, my limit, excuse me. I'll get sine of 2x divided by cosine all over x. And then I wrote it right here that that is just, x is just x over 1. Well, we have a fraction divided by another fraction. So we multiply by the reciprocal. That's how I got the limit as x goes to 0 of sine of 2x divided by cosine of 2x times 1 divided by x. All right? I just flipped it. What else? Oh, yeah. I want sine of 2x over some multiple of x, right? Preferably 2x. So if multiplication is commutative, right? A times B is B times A. So cosine of 2x times x is the same as x times cosine of 2x. So then I can rewrite line 3 down here. So I get that the limit as x goes to 0 of sine of 2x divided by x, divided by x, times 1 over cosine of 2x. Well, we can use what we learned from the previous problem and multiply by this fancy 1. And here's my fancy 1 right here. It's 2 divided by 2. So doing that allows me to be able to use the limit that I already know of sine of 2x over 2x as x goes to 0 as 1. So then I could have the limit as x goes to 0 of 2 times sine of 2x divided by 2x times 1 over cosine of 2x is going to give me 2 times 1 over 1. Cosine of 0 is 1. Multiply that out and I get 2. Awesome. So give these a little bit more of a practice. You have a few of them in your homework. I'm sorry if you don't like the pre-written lectures. I tried to make them not pre-written and have them write along. So hopefully I'll figure this out the more practice I get recording these. So let's hope that this lecture actually recorded. All right, I'll see you guys in 2.5.